me co-host.
Oh, Agnes, you're not a co-host?
No, maybe because my connection went down before.
Okay, absolutely. Just a second.
So that I can record. Thanks. Okay, let me just start. So we will start the last session of today, which will be made by the talk of Sabrina, and then there will be the discussion, so it will be all in a row. But okay, for the moment, let's start with Sabrina Pasterski, who is talking about celestial pyramids. So please, Sabrina.
Thank you. Well, it's a pleasure to be here, and it's nice to see everybody. I wish it was in person, but always nice to get together. So today I'm going to be talking about work with like 4 papers with Andrea, and also the pleasure of working with grad student Virgo and Emilio, who's going to be leading or leading the discussion session right after me. So in each of those papers, we're basically looking at basically spin shifting relations and conformal multiplet structures. So that's the title of this talk is going to be just, I guess, a graphical description of basically the ascendancy relations and SUSY relations that tie together various soft theorems. So that's what the name is coming from. Okay, so just because I drew a pyramid and a sphinx on the other side, I should remind that we are in Greece supposedly right now, so it's a slightly different mythology. And ironically enough, I guess, or like you can force it to be true, of course, our subfield is basically some variant of the riddle of the Sphinx, where we're studying quantum gravity in 4 dimensions, but we have a 2D description. And then depending on if you want to look at null infinity, that U direction or the like behavior in delta makes it look like it lives in 3 dimensions. So we know the answer to the riddle of the Sphinx. Now we can go from Thebes back to Corfu. And today the outline of the talk, the goal for my talk is going to be trying to emphasize within this conformal multiplet structure the connections to various things that a lot of people here are talking about or working on. So while the content of the slides, you might see some overlap with what I was saying at EEST and developing that like sense, like whenever we're talking about things, let's try to keep in mind how to relate it to what you guys are doing. So that's going to be the main goal. But the outline for now is we're going to start with generalized primaries and then celestial operators, how we define them via this inner product with these primaries. And then moving on to the celestial diamond structure with Emilio and Andrea. And then finally, how they tie together into the celestial pyramid. So that's the outline for today. So let's just get right into it. Okay, so starting with the definition, which is familiar to a lot of those who are on the celestial amplitude side of things. Basically, so a conformal primary wave function is going to be a function of a bulk point and a reference direction. And we want under a specific transformation of both the bulk point and this reference direction, which we think of as living on the celestial sphere. So I'm in 4D right now, has a certain transformation property. And so if I normally have, in a lot of the papers with Shuhong, for instance, we were looking at basically S equals J, absolute value of J. And so that's restricting you to radiative conformal primaries. But if you look at massless scattering and you relax that, that's where you're going to be able to get the structure where the celestial pyramid is going to be a function of S, delta, and J as the 3 directions in which you can move around. So for radiative conformal primaries, I'm not going to relax that. I'm going to say that it's for massless guys, S equals J, they solve the appropriate source-free equations of motion. And this representation here is for that corresponding velocity. And then for generalized conformal primaries, I'm going to relax a lot of that. Now, in some instances, I still want it to be a solution of the equation of motion so I can construct the appropriate external particle states. But there are interesting contexts where you're looking at non-trivial backgrounds corresponding to shock waves or whatever, where you can construct something that also transforms in this manner, but will have a source. Okay, so then what one can do is, of course, if I want to construct my dictionary, so my local primary operator is defined in terms of if I have a bulk local operator in inner products, and also my conformal primary wave function, then I can construct this operator that manifestly transforms like it should as a conformal primary in 2 dimensions, or D-2 generally. So one thing to keep in mind here is that formally speaking, if we were in the free theory, we could of course do this on any Cauchy slice. Now we want to study theory of quantum gravity, so we should really be worried about saying that there's this bulk local operators. But in practice, if we end up pushing our Cauchy slice to the boundary, we're essentially saying that these However, the theory is behaving at null infinity is in some sense free. We have this like boundary description of those operators. So the nice thing about this is this can be kind of phrased to set up a basically extrapolate style dictionary where you're just tethering the fields at the boundary. And then by performing the appropriate convolution in terms of this inner product between free solutions to the wave equation, you now have this manifest the transforming the right way object that you want, that you say is the celestial primary. So this step is important also for understanding, I guess, elements of the, like understanding quantization in the Hilbert space, et cetera. Like it's nice to have both a 4D picture and then a 2D picture of every step that you're doing, so you can kind of see what makes sense. So one thing that's slightly fun about it is, if anything, you'll see with Banerjee's part of the discussion session today, is that you can get a lot with even just the global symmetries. And so the starting point that we're going from is inspired by some of the earlier work of Banerjee, and you've seen what he's done with it since, where he's a lot of powerful constraints on the like differential equations that correlators have to satisfy. So what the nice thing about it though is it basically you can tie a lot of statements down just to things that hold from the level of the kinematics and the symmetries that you make manifest by your choice of external scattering states. And so essentially I could say one of the themes of the works with Andrea and also early with Laura is to kind of pin down kind of aspects that come from the level of that kinematics that are just kind of guaranteed by looking at the wave function. So it's kind of nice. And then with this picture in mind, we also have now a bulk interpretation of these states that we're creating. So again, you can kind of like use it as a reality check for if you want to make a claim about this 2D CFT, and if you're changing, for instance, like in Andy's like state operator correspondence shadowing the out state, what does that mean in the bulk? You know what it means. So you can kind of like try to pin things together because you know both sides of the dictionary, or you know where you're making a change to certain assumptions there. Okay, so now if my task is just, I want to build up these wave functions, right? So I can do the fact that, okay, I'm not going to say that I need my 4D helicity to match the value of the spin. I'm just going to try to write everything down so that there's these 3 labels that it transforms covariantly under. What I would do is I need the following building blocks. The first thing is my scalar. So the scalar guy, the standard Mellon transform of the plane wave gives you this 1 over negative q dot x to the delta. And then of course, because x is a Lorentz invariant, it's basically the only Lorentz invariant you have sitting around as a function of the space time. I can just multiply by a function of x squared, and you know that that won't change the covariance properties that I was demanding on the previous slide. However, of course, it will change whether or not this is a solution to a given equation of motion, so it's important to have that there. Then if you want to add in basically there's a bulk spin, which would be this index mu, or the spinner index, or a boundary spin, which is the value of j. Those aren't necessarily the same, and one can see that by basically breaking down into a covariant tetrad, a big basis for the tangent space and Minkowski space. So what we're basically doing right here is we're just writing down a standard normalized orthonormal tetrad for Minkowski space that also respects the standard transformation properties that we defined before. And so one important thing about this, like generalizing the definition, is that of course, when we're talking about constructing external states, we want our wave functions to satisfy the appropriate equations of motion. But if we want to just write in terms of building blocks, then these individual building blocks won't necessarily do the same thing. So right now what we see is like basically each of these guys will have weight delta, so they won't change the weight of the wave function, but their spin will be plus or minus 1 for these radiative guys, and basically these longitudinal guys, which you'll see in certain shockwave solutions, are delta equals 0. So they have the standard orthonormality conditions, and they further decompose into a spin frame. And so this is where the other part of the talk with fermions comes in, is basically I want to also look at wave functions that now are spinner value. So we can do that all within this framework of saying demanding covariance properties and pushing through with it. Okay, so for a given spin, like, so I fix my value of S for the bulk field. And so I know that I want this field to transform in a certain representation of the Lorentz group in 4D. Then I can construct wave functions with any j less than or equal to S, which is like either integer modded or half integer modded spin, by just taking tensor products of my scalar, my free function of x squared, and my tetrad and spin frame, and like sums over the independent versions of those that I can build up. So for the case of this is just trying to show how you reproduce the stuff with Xu Hung, which is the radiative guy with spin 1, will have my spin 1 tetrad element, my free function of x squared, and my scalar primary. And for delta equals 0, whatever delta, but j equals 0, I have two possible linear combinations that I could do. So then I take that ansatz, which is just from the symmetries, and now I say, okay, I want it to satisfy various either gauge conditions or the equations of motion. So the equations of motion is the more important one here for the construction with that inner product. But one can see essentially from the first line that the act of saying that this radiative wave function, which is source free, is actually a conformal primary, is itself basically a gauge fixing condition. So the consistency of radial gauge and harmonic gauge was something that we were like lucky in the paper to shoot to see that it was a consistent when it's source free. And here, basically, I think a nicer approach is to say, well, that is kind of like the gauge fixing that you're doing. So of course, when you actually talk about the operators, if you're not looking at correlation functions, like you can, there will be like gauge transformations in those transformation properties in the Hilbert space. But basically for the external states, we can make a gauge choice, which is saying it's conformal primary. And so then, of course, you have to satisfy now the equations of motion in that gauge, which are just now the harmonic equation. And when you do that, you get two solutions, which are, of course, the shadow and the non-shadow primaries. So that's the route for the radiative guys. And now when you repeat it for the non-radiative guys, curiously enough, this system of equations actually does have a set of unique solutions. So if you want to satisfy everything that the radiative guys satisfy, for this non-radiative guy, you're going to really just isolate yourself down to what we're going to see is related to a descendancy relation in this celestial diamond picture. So J equals S, and primary amounts to gauge fixing. And we have that our radiative solutions have these two options, but any value of delta is allowed. And of course, delta on the principal series and like was shown to basically capture the finite energy radiative states. And with Laura, how to analytically continue off the principal series there. So now, of course, the question of operator spectrum is actually twofold. And this is something that was very nicely like raised by Andy, Laura, and Andrea at one point, is basically to understand what's happening in the conformally soft limit. So first of all, you have issues with shadow redundancies that are appearing in that limit. And then also the fact that when you look at delta off the principal series, that's where you get these currents that you're seeing, like the stress tensor comes from delta equals 0 shadowed. So I would say that there's two questions for the operator spectrum. The first one is, okay, so I'm still radiative, but my values of the conformal dimension now seem to need to be off of the principal series. What do you do? And the paper with Andrea and Laura, we were trying to address that as this analytic continuation of the data on the principal series. So like you're not over complete. So then the papers that I get to present today are about the second question, which is what's the role of the wave functions such that the value of J doesn't match the value of the spin, even though you are massless. So it's not like you're just projecting a polarization tensor down in the massive case, so that's like not like aligned with the normal to the celestial sphere or whatever. So basically now what I want to say is for the first situation, what we were looking at originally is the special principal series guys not only have this feature where if you look at the 2-point function, you have this orthonormality condition on the principal series, but you also have the appropriate space-time fall-offs for the contact terms, and for the shadow, you have it for the non-contact terms. And so from the point of view of someone who's looking at the asymptotic symmetry analysis and saying, well, I want to make sure that I'm not just looking at solutions that are not really in my physical phase space because of the boundary conditions for them, there's this funny constraints in the spectrum in the following sense. So basically, if you wanted to do your extrapolate style exercise implicitly in all of the soft theorem derivations, we're basically saying, okay, I can show that the ward identity equals a soft theorem because I am taking basically looking at not the expectation value, but the action of my operator, which I know in space-time acting on my Hilbert space, and that involves taking a large R limit, which induces a saddle point. And so implicitly, if you do that saddle point and then you're Mellon transforming, there's a certain order of limits there with the values of the conformal dimensions for which that converges. And so you'll see the principal series is also kind of just on that edge, or like which it needs to be, because you have like basically if it fall off too fast, it wouldn't be there. If it felt like if it grew too much, you'd be worried about it. Where the saddle point for these non-shadowed voids is what you would pick out in that order of limits, and basically gives you this operator supported a long future null infinity, say, for the outstate. And so the question of what values of the conformal dimension you want to look at is not so innocent in the sense that, like, okay, fine, I can worry about completeness. Like basically, one should be worried also about the physical implications in phase space and like the boundary conditions for these guys when you're changing the values of delta. And so that part of that question is interplayed here, and that's what I just wanted to emphasize. So for the most of this talk, though, I'm going to be worried about the second part of the question, or basically, like, because we're coming up with these various issues. So first of all, delta off the principal series, somehow it's not part of the basis. Also, there's concerns about whether or not it falls off appropriately in space-time, but I somehow need it. I also see these shadows that are appearing. So these kind of like this culmination of different questions regarding these conformally soft limits leads you to try to look at also the non-radiative guys, because they're going to be connected through these ascendancy structures. So that's what the purpose of the talk is today. Okay, so I want to be able to analytically continue off the principal series. And for various special values of delta, I find that there are pure gauge modes. And so another question that arises is the following, is that basically the leading and subleading gravitational soft theorem, leading E&M soft theorem, and same thing with the gluonic case, there are certain soft theorems that are kind of easier for you. Like you kind of already know what the asymptotic symmetry is, and then you can see that the work of Pigling and Lada had to dig a bit harder to find an asymptotic symmetry interpretation for the subleading guys. Now, I'm not going to say anything about like a no-go on that, but I will say that when you say that I'm gauge fixing to being a conformal primary, and then just trying to read off what value of the spectrum it becomes pure gauge, in that case, you're guaranteed to have basically what amounts to the soft charge operator. So if I just did a very naive Chung et al. Style, here is my wave functions, where is it pure gauge? I can read off for you all of the quote unquote the universal soft theorems, which also don't have as many subtleties with how they give loop corrections, etc. So this is not a no-go. So I'm not saying that you can't have an asymptotic symmetry interpretation for the others, but as far as a conformally soft or conformally covariant asymptotic symmetry interpretation, the easiest ones are these guys here. And so part of what I'm also going to talk about today is to try to unify all these extra soft theorems with a structure that kind of incorporates them nicely, rather than seeming like they are the odd ones that don't quite fit in. So what I'm just saying right now is, again, connecting both the supersymmetric versions and the non-supersymmetric versions. So we have, it's been one, just the leading soft theorem, gravity has the leading and subleading guys. And then at supersymmetry, the spin 3/2 guy also has a pure gauge version of the soft theorem, and that was a recent paper with Yorgo and Ingrid that we're looking at. So that's nice that we can quite easily look at the large R behavior of this guy that we know is pure gauge and literally identify the wave function as being, okay, yes, this induces a large pure gauge. And so I'm literally just looking at the profile for the field at infinity and seeing that it matches the Goldstone mode for the corresponding asymptotic symmetry from the point of view of just what its 1 over R follow-ups are. So you know what this is from the wave function, you know this because it's pure gauge. And so basically the fact that it then is a current is also guaranteed for you, but the fact that it's this given soft theorem, you have to do a little bit of work, I guess, to see that, again, it's kind of can be guessed from the conformal dimension that this is the right value of the power of omega, but like the work by various authors, things like Andrea, Alfredo, and Kate and Anna, showing that you can extract that soft theorem rather than just see it if it's like dominating with a pole in delta or something like that. So that's all good. But of course, there are basically there should be a more general structure that can account for not only these guys, but also those most subleading soft theorems and this infinite tower like W infinity that's been the hot topic right now. So we want to basically talk about celestial diamonds, which are, Emilio is going to go into a little bit more detail about the classification program from the point of view of CFT, why like you would look at primary descents, etc. But essentially, if you kind of are inspired by the work of the early work of Banerjee, you can notice that a lot of the structure is actually can be found just by looking at the global conformal multiplets. And then you see that there are necessary relations between various soft modes and their shadows, or various soft modes of different helicities, as well as these non-radiative solutions that were appearing from like solving basically everything you could demand, except for the fact that it's not J equals S. So a primary state is going to be annihilated by 2 of the Lorentz generators and have definite weight under L0 and L0 bar. And then I'm just taking W derivatives to descend and look at the global conformal descendants on those guys. And when I do so, I can sometimes, depending on the value of the dimension, find a primary descendant. And so in the context where basically that primary descendant is 0, then you really do have these finite dimensional multiplets. But in other contexts, it's not obvious that that primary descendant is actually null in the standard sense. And this has to do with a little bit of the inner product in the Hilbert space. And this is something where effectively you will get basically contact terms that we're going to see later. Oh, Andy has a question. Yeah.
Sabrina, can you comment?
Yeah.
So the right-hand side of your diagram is, I guess, positive helicity, and the left-hand side is negative helicity.
Sometimes, I mean, it's a little bit, it's either the shadow of it or it is vacuum.
I guess that's kind of my question. So how are we supposed to think about the fact, we usually would think of those as independent fields.
Yeah.
But now in your picture, when you go all the way down to the bottom, you get the same thing from a positive helicity and a negative helicity. Is that saying that they're not?
That is saying it for the leading cases. So what's happening is the following. So right now, when I'm descending, I am descending from the delta equals 0 soft theorem on one side, and on the other side, I'm looking at the stress tensor. So those guys are related by this shadow operation. And so one thing, so that doesn't impose a helicity relation. But one does find, though, is that, of course, the leading.
Wait, the left and the right are related by, wait, which are shadow?
So the left and the right are going to be related by shadow, but the left and the right are not the Mellon transform primaries. They're literally the shadow primary. So the only case where you have a helicity redundancy is the leading soft theorem. So basically the same way that the soft theorem for the plus helicity.
Sorry, I didn't understand that sentence. I thought the
Yeah.
left and the right were the usual Mellon primaries.
Not in this, no, only for some
Not
of
in
the,
this
only
picture.
the leading one. Not in this picture, not generically. Not generically. Which is good, because basically what happens is that you need, like,
But this
so
picture would be, this diagram would be true if they were the Mellon primaries, wouldn't it?
No, wait, so here's what happens. Okay, so if you look at the Mellon primaries, then the other corner is its shadow. For the leading soft theorem, that is the other Mellon primary. So there really is a redundancy, and I think the best way to handle it is to look at the dressing modes. For these guys, you have basically the memory and the Goldstone diamonds are basically sitting right on top of each other. And so like you have the stress tensor, and then you have the dual stress tensor from the paper with Adam, for instance, sitting at that corner.
I see.
On top of each other, which is good, because I mean, it kind of shows that for the leading case, you really do kind of have to add those Goldstone modes to your face space. The guys that I'm going to say are at the top of the diamond, and then these shadows never need to be put in by hand. So basically, it doesn't conflict with those observations, but it does give a kind of natural interpretation for certain effective field theory models for what will be at the top of the diamond, for instance. And there, one can avoid introducing shadows by hand. Now, of course, there are natural situations where you want to shadow or smear to make these like correlators not singular. But from the point of view of a purist saying, like, do I need to do this? Can I say that my dictionary is this local operator, is this Mellon transform? Or do I need to, like, it would be a problem, I would say, to say that I only have my local operators being Mellon guys, and then every once in a while for the current, I need to smear it because now it's this non-local operator in the CFT. So if you say instead, I'm going to add a local operator at the top of the diamond, then it's going to descend to the ones that you need. And so basically, like, it's a moderate change to the dictionary as opposed to smearing everything, for instance. So that's one approach to this, but it won't get in the way of the intuition that you have.
So there are two pictures, there are two diamonds. You could have another diamond where you shadow everything on this diamond.
Exactly, and they're sitting right on top of each other. So for instance, if I guess it'll be easier maybe when I have like numbers at these things, but like you can have a state here and then the shadow state for that delta right on top of it, but its shadow is the one with 2 minus delta, right? So like the H tilde sub O from 0 versus H sub 0 are like not shadows of each other, but they're the shadow mode of the reflected guy. So.
And is the light transform moving us up the diagonals?
Indeed, it does. So from the point of view of the group theoretic person, like you can see that the shadow is basically a double wall reflection. And so, I mean, maybe you can also argue that that's necessary for SL2C versus SL2R versus SL2R, but the analog of the light transform up to an appropriate regular, you have to regulate it a little bit to make sure that it works. It's a Green's function for the, for just flipping up one of them.
Where is that explained? Is that explained somewhere?
Hopefully to come, and that's where like there's a lovely paper that I hope that we could just like say but yeah.
Thank you.
Yeah. So that'll be worked out, and essentially it's a small change to the nice observation that Tool also has. So like that's where I want to say later. But basically, so essentially what's happening there is you have the shadow you can think of as a Green's function for certain differential operators, which in the shadow case, it's basically you're inverting one, then descending again. But you can also think of just inverting one leg or the other. Okay, so I don't want to get too far into this aspect of the Hilbert space inner product, because I feel like there's others here who also have studied this more in depth, and maybe Emilio can point on this more. But basically, one should be just slightly cautious of saying that if it's a primary descendant, that it's null. Ideally, I think one does want to, so I'd say that there's kind of two philosophies within celestial CFT. There's the one where I say, I am going to stick with what I have and use my 4D dictionary to build up some 2D guy and reassess everything I know from the yellow book at every step that I'm doing. So when I do that, then like, just because I would take it for granted in the 2D CFT context doesn't mean I should. Then there's the kind of purist, or like maybe not purist point of view, but there's the other point of view where can I make this 4D problem look like a standard, not vanilla, but maybe chocolate and melon or whatever, like slightly exotic, but more like a 2D CFT. So if I do that, then this is where you want to smear operators and everything. You want it to be like you don't want the low point functions to look singular. And on top of that, you probably do want to have some analog of your state operator correspondence where you understand how whatever you're doing to the outstate really does give you the standard like L's and L bars, that conjugation should affect them in the same way that it does in 2D CFT. So I think it's fruitful to study both approaches because in the end, it's basically some sort of intertwining between different representations of the same structure, which is the amplitude to begin with. But just pointing out that as it is, the way that the Hermitian conjugation works on these operators Li doesn't enforce you to have basically a zero inner product when you are a primary descendant. So just keep that in mind. But it does end up behaving in a very similar way in the sense that the guys at the bottom of the diamonds will essentially only reduce to contact terms in correlators. And so that's very much like operator equations in 2D CFT. So I think that there's nothing there conflicting with the fact that there could be a natural interpretation where primary descendants are null like in 2D CFT. So just saying that, but it is something where one should be a little bit careful because the kind of fun thing about it is that some of these descendants are manifestly not zero as far as wave functions are concerned. And so then you want to understand why those wave functions are reducing to contact terms. And then that will tie nicely, I believe, into the BMS flux stuff that like Laura just had a paper on, and then hopefully I think Barnett is going to be talking about today, or not today.
Sabrina, you have 5 minutes.
Oh, sorry. 5
Yeah,
minutes.
5
Yeah.
minutes.
See, that's why I was very, I cut these slides out. Okay, so let's just go through this. Perfect. So, okay, so we have an infinite tower of radii of primaries. Okay, so when we just do that classification, we actually have a full tower of those values of the normal dimension. And so you have these W infinity guys coming from, I think it includes these soft theorems that I'm most interested in, but also extends to ones where basically you descend to zero at the bottom of the diamond. So for values of delta that are negative enough, you can see that the 1 over q dot x to the negative delta is like to an integer power. So you can take enough W derivatives, it's going to give you 0. So that's essentially how you see that. And so, that structure of the conformal multiplets is you have this primary at the top, and each of the left and right descendants just vanish. What'll happen though in the case where there's soft theorems is you're going to have the primary that is the conformally soft theorem being either the left or the right corner of the diamond. Its shadow is going to be at the other corner, and then they descend to the soft operator, and that structure was first investigated by Banerjee, for instance. And so the nice thing about that basically is that when you see the descendancy structure, then you can also kind of lift it up and then try to interpret the top of the diamond and the bottom of the diamond as basically these paired modes. So when you look at the conformal dimensions in the BMS flux literature, what you're seeing is you're seeing these weights corresponding to either the top of the diamond, which is the Goldstone mode for them, or the bottom of the diamond, which is its symplectic partner, which would be the charge mode. Now, the fun thing about it also when it comes to trying to connect this to the story of OPEs and like these global symmetries is that essentially what's happening is right now, I'm just looking at the soft operator. So I'm basically taking all the soft theorems and descending down. The constraint equations, of course, relate that to other hard operators, which have to be sitting at this value of the conformal dimension to have a non-trivial like ward identity. So basically you have something that's a primary descendant plus something that's not a primary descendant equals 0 in your S matrix element. And so if you smear that object with something where it would be annihilated by the kernel for these descendants, then you're going to get your global symmetries. So that structure is that's how it's just that kind of nice that you can look at the descendancy structure and kind of see the same things that are very important to then finding these recursion relations for OPs, for instance. So I just want to emphasize that like we're doing this kind of very like kids exercise, maybe like looking at derivatives of things, and we're seeing all these very nice structures coming out. So so the shadow relation was one to emphasize, but I think we talked about that with Andy basically now. And then of course the stressing and the soft thing, these two diamonds on top of each other is what I was just mentioning. So for the sake of like just at least getting through all the pyramid part of it, there's one degenerate case where basically for the most subleading guys, you are descending from one primary to its shadow. And so that has been the subject of more recent investigation because it's the one where you expect there to be some sort of symmetry interpretation, but it's somehow just not quite there. And these are also the ones that give you some interesting recursion relations for the OPs. So just pointing out that they are descendants makes it a little bit easier because then you only have to do one computation to evaluate the soft charge, for instance, because you can take derivatives to find the other. So that's just one thing to point out. It's about the degenerate cases, you're moving from the top of the diamond for very negative integer values of delta to the left or right corner, then down to the bottom, like basically instead of to the bottom, it degenerates to this, like it is both the bottom and the top corner because of this tilde could be, you could shadow both of them and it would also be an operator at the bottom of the diamond. So basically that's the nice structure there. We can go through the leading soft theorems if we want to, but for the interest of time, I'll just be brief because I think some of the stuff was said. Basically for the leading case, there is this shadow redundancy between the two guys. And so you see that coming from, if I just added a dressing mode at the top, that it would basically manifestly make that for you. And also the same conformal dimension for the top of the diamond corresponds to an Eichelberg sexual geometry. So if you're interested in chalk-like solutions or non-trivial, non-perturbative backgrounds, that's your go-to guy. For the subleading soft graviton, you no longer have the shadow redundancy, but you do see that the stress tensor and the dual stress tensor are basically on top of each other as different diamonds. They smear from, the stress tensor smears from the delta equals 0 guy, and that then those basically, like you can basically include both the stress tensor and its shadow by including basically a diffeomorphism mode. And this is the one that I believe like Kevin and others have studied, which is this like spontaneous symmetry breaking for this diff-S2 mode, parameterized in terms of like essentially like a vector, like a y of z on the sphere that's like spontaneously broken. So you're looking at like the super rotation or the diff-S2 vector field mode breaking to one or the other symmetry. Okay, so then of course the nice thing about what I want to say for the purpose of the title of the talk is that you can extend this to any spin. And if you look at this, they look like they almost want to be on top of each other, especially if you look at the 0 and the delta and j values for the center of those guys. And so for one thing, which is kind of what I mentioned, is that the top of the diamond, you have this dressing. You can look at the conformally soft sector and have some interesting EFT interpretations there. And similarly, that's where the levels come from. But for the purpose of this talk, and so I don't not give justice to this lovely work with Andrea and with Yorgo, we were all in most of this talk, I've been talking about just moving within the same value of the spin of the field, but different values of J. And we found that there are nice interpretations where it still is a spin S field, but now J is going to be less than S, and it corresponds at the bottom of the diamond where there's a soft operator charge, at the top where there's a dressing, and it descends to the radiative guys. You can also move between values of S using Taylor and others have developed, which is these SUSY just supersymmetry in the melon basis. And so what one finds is that basically I have all of these individual SL2C descendants, and then they're stacked together and tied together with the supersymmetry relations. And so nicely enough, that explains why, like, if you look at the diamond, the soft operators sitting here or here or here, essentially all come from different values of spin, but like the rightmost, so like the positive Felicity soft theorems. And then the reason why the parameters for those charges are the same when you write it in terms of like making an isomorphism between the Ward identity and the soft theorem is because basically they're descendant that you have to descend a different number of times down to the soft operator, but the same number of times up to the shadow, for instance. And so you can explain some nice properties there on that, but I won't go too far into it for the sake of not bleeding into the discussion session. So what I want to close off at the end is that basically, hopefully I did a little bit of what I promised, which is present the celestial diamonds and how they tie together into the celestial pyramid in a manner that reflects some of the interesting results that other people at this conference are talking about. So thank you guys so much for your time, and I'm happy to take any questions.
Thanks a lot, Sabrina, for your talk. Any questions?
Anna, hey.
Hey, thanks for the nice talk. So I'm wondering, maybe this is a hard question, but do you have any thoughts about how these interesting structures would affect conformal block decompositions?
Yeah,
Like,
yeah. Okay, so so yeah, definitely. Okay, so from the point of view of the particular soft operator, so like I want to say that like for instance, when I write these shadows down or these like light transforms down, I'm implementing the Weill affection at least when I'm at the special values of delta where there are two primaries. So you can see in the case of so in a case where you're in the leading soft theorem, you can see that that light transform would basically invert you to a correlator of the top of the diamond, I believe. I don't have much more to say. I think if anything, I think you're probably exploring that aspect of it more. But I do think that, for instance, if you do have certain smeared correlators, you can naturally identify some of the operators for, like when you take the value of the dimension for the smeared guy, you will see that you've accidentally lifted yourself up to a correlator of the top guy. That I know that much, but I don't have much more to say beyond that. And so I feel like hopefully everything we're doing will be complementary instead.
I'm essentially just wondering whether you think that any of this may affect, like if you do conformal block decomposition of a generic correlator, you're going to see like the coefficients generically won't factorize, but they will be sort of like linear combinations of finite number of terms, which are going to be which are going to look like they factorize. So this sort of suggests that there is some kind of degeneracy, like at each exchange dimension. And I'm wondering whether you think that any of this, like which, if any of these parts could explain this kind, perhaps, and this non-factorization in some sense, or.
So the statement that I just want to say right now, which I think I don't want to say anything that I'm not like 100% sure on. I would bet that if I look at correlators which are appropriately smeared to make them not distributional, then I can take the values of the conformal dimensions for like going to certain soft limits literally is lifting me up to basically looking at correlators of operators that are strictly in the conformally soft sector. So what I mean to say there is that basically definitely there is an interplay with these, because basically what I'm saying is with the bond. So if I say that I'm shadowing or if I'm smearing and I'm literally moving up the diamond for the case that my deltas are the special values, then the funny interpretation of that isn't just that there's this conformally soft theorem at those values of delta, it's that I'm literally scattering these parent primary. So I'm scattering like this spontaneous symmetry breaking like Goldstone mode when I take the value of that delta. And I think that is a slightly interesting difference than if I were just doing the same thing with a conformal block decomposition without doing any smearings and taking the values of delta. Because basically there, I know that this is like the Goldstone mode for some spontaneous symmetry breaking guy, and maybe I can say something about the sector. That's all I want to say now, because that basically I know that it's using the diamond structure and there is a natural context in which you're already doing the smearing, but then now you've restricted that smearing to a value of delta for which you're literally moving up the diamond. And so then with that insight, you can say, okay, look, this is really a correlator of these other guys. So that's the extent to which I know and or can say at this point. So I'd say, yes, there's a connection, but I feel like there's something that a lot of us can work out in different ways. So.
Okay, yeah, thanks. More question for Sabrina?
Yeah.
Andy?
Yeah, so these diamonds seem to mix up, but maybe it's an illusion, but they seem to mix up the left movers and the right movers.
Yeah.
And is it clear that the left moving soft theorems are the left moving currents and the right moving currents are independent, or is it still clear with all these relations? Or
so within these, within the global descendants, you do not have any sort of mixing except for the leading soft theorem. So from that point of view, one would expect that possibly if you appropriately dressed everything, so you can definitely dress, you can look at the dress operators that are essentially neutral under super translations, for instance. And even though I don't want to advocate doing that necessarily, if you did do that, then I think you'd be in a sector where every soft theorem is independent, but maybe there's issues from like double soft limits. I don't want to say anything there that I'm not seeing from my just symmetry multiple structure. So from the structure of the global descendants, you do not see any sort of talking except for at the leading guy, which I would remove with addressing to make it neutral. But obviously, of course, like one should be careful about like using Virasoro descents or whatnot. Like, I mean, I can imagine that there's subtleties there because there you're descending with another soft operator. And so like double self limits are important, and then the algebra can get like larger. So so I don't want to talk about the multiples intersecting after that statement.
Thank you.
So if there are no more questions, maybe we can move on, and then Sabrina will pop in
Actually,
again
I have
after.
another question.
Oh yeah,
Sure.
Was there any sign of the two-dimensional supersymmetry algebra?
So yeah, so I think I want to probably defer. I mean, so the computation that one would do is basically using the OPEs that are in Taylor's paper, and then looking. I believe that that's what Pate and others have done. I mean, so playing with it roughly before. I mean, like it's they've done this nicer paper. So that I don't think you see from the interactions from effective field theory that are consistent in the bulk and 4D, the appearance of what would be like a world sheet SUSY algebra. But I do think that I should probably defer to Taylor or Pate and their co-authors for saying that precisely, because you can just look at the structure of the algebras that they're finding, and I'm basically just repeating that. In this context, so what we were doing right now is basically just adding on top of that the fact that like now you know that you're going between these shadow guys. So all we've added is essentially a little bit with the you have their relations, or at least Taylor's relations for descending and ascending between the primary operators, and then we can see with the diamonds how they interplay with the shadow. But I don't want to speak for them because I believe I think I'm saying the result accurately, but that's their baby. So
Okay, thank you.
Okay, thanks a lot, Sabrina. And now we will start our discussion session. Andres, can you make Shamik co-host maybe?
Absolutely. Let me just find Shamik.
Okay, so just a couple of words how the discussion works. So our idea is to have first our two panelists to present to start off the discussion for about 10 minutes each, and then these 10 minutes will be uninterrupted. So please no questions at this point, and then you will defer all the questions later, and everybody will start discussing. There will be all the speakers of today, and we can all discuss. So the idea is to have these 2 10 minutes talks, and then there will be a discussion where everybody can participate. In particular, also there can be questions to all the speakers of today. So maybe we can start in alphabetical order. So if Shamik would like to start.
Yeah, sure. Thanks. Okay, so let me share the screen. Okay, so
yes, sure.
Yeah. Well, how do I? Okay, just a minute. Okay, no, yeah, it's fine. Yeah.
You should be able to share, I guess, because you made co-host.
Okay, just.
Yeah, Shamik. Yeah. Perfect.
Yeah, is it?
Yeah, we can see your screen.
Yeah. Yeah. So is it fine now?
Yeah, perfect.
Okay, thanks. Yeah, somebody. Okay. Yeah, so I'll just, well, so this is a brief thing. I think I have only 5 slides. So I think lots of these things have already been talked about. And so I'll start by mentioning the basic facts. So the basic thing is that in 4-dimensional flat space-time, the asymptotic symmetries are in infinite dimensional. So they act on the S matrix and the word identities for these symmetries are the soft theorems. Okay. Now so since this is supposed to be a discussion on bootstrap, so let me just frame this question. So the first question that I would like to ask is that can one bootstrap the S matrix in 4-dimensional space-time using the infinite symmetries, and in other words, the question is that to what extent can one solve for the S matrix using the general properties of the holographic dual. So, so I'll just discuss one example, and this is the example of the three-level MHV graviton scattering amplitudes in GR. So now using the infinite dimensional asymptotic symmetries. So in this case, we basically get one copy of the Vitasro algebra and SL2C bulk bar current algebra super translations, and an infinite number of other soft symmetries. So now what one can show is that if you use these symmetries, then you can write down differential equations for the MHV amplitudes, and they look like this. So this is the standard S matrix in the Fock space, and these are the differential equations that we have. And it turns out that if you have an endpoint MHV amplitude, then you have n minus 2 such equations. Okay. So the thing is that so how does one get these equations? Now these equations arise due to the decoupling of primary descendants of the infinite dimensional symmetry algebra. And in particular, so it also shows that, well, in some sense, the holographic dual theory, which computes the MHV amplitudes, is a chiral CPHT2 with infinite dimensional global symmetries. So in particular, so this W in infinity is there. Basically the existence of these differential equations, so that shows that this dual conformal field theory, so that can be successfully bootstrapped like the minimal models. And the interesting thing, I think, which is different from most of the S matrix bootstrap here, is that this is basically bootstrapping the massless scattering amplitudes, which is hard to do in the standard way of doing the S matrix bootstrap. But so this is an extremely special case. But the thing is that I just wanted to give this example to show that like how things could actually work. Yeah. So, and it turns out that one can do the same thing for the gluons, and these were done here. Okay. Well, so now this is a last slide, and I just want to mention one important difference from bootstrapping the standard conformal field theory and the spatial conformal field theory is that the scaling dimensions of primary operators, they don't need to be bootstrapped because they are not fixed, and we can take any value for them. So that's one, and this is an important difference which hopefully makes a job of bootstrapping the spatial CFTs simpler, and I think it will be extremely useful if one can develop techniques of incorporating the asymptotic symmetries in the standard framework of doing the asymmetrics bootstrap. Yeah, so I'll stop here. So this was the last slide. Thanks for that.
So thank you very much. So maybe now we can have Emilio.
Yes.
And then we will have all the question sessions afterwards.
Hi, can you hear me?
Yes.
Hi, everybody. Okay, let me share the screen. Let's see if it works. Does it work?
Yes, it works. So now Emilio Trevisani will present something about celestial diamonds.
Okay, so I would like to thank the organizer for this very beautiful workshop and for the opportunity to give a talk. So I'm gonna also talk about celestial diamonds, and since we already had a very beautiful talk by Sabrina with a lot of details, I decided to make a very schematic talk. It's gonna be like a cartoon in practice. So this is about these two works in collaboration with Sabrina and Andrea, but I'm not gonna reference any other paper, but I want to say here that this is also based on a lot of ideas that were already present in the community, in the celestial community. So let me start by a very short motivation. So we know why we care about celestial CFTs, but let me tell you what we are doing here and what is the motivation. So the idea is that, okay, we have this change of basis and we can map this as matrix and write it in terms of something that really looks like a correlation function in a 2D CFT. And in particular, the good thing, one of the good things of this map is that soft theorems can be mapped toward identities and similar soft modes to conserved operators. So the motivation of this talk is that so we would like to understand the soft sector and asymptotic symmetries, and this is in general like some kind of hard task. But what we can do is like using this map and in practice map it to this question. And this would mean like that we just want to classify conserved operator, special operator in these celestial CFTs. And so the main idea is that this is very simple task in some sense, because this classification can be just done in this way, like by finding the primary descendants in a CFT. And this can be done in any CFT, in any dimension. It's I give here like one very simple example. If you take a spin 2 operator and you ask that this descendant is a primary, then you get that by default, you know the dimension of this operator that is equal to D. And indeed, this would be the dimension of a stress tensor. And indeed, this thing would give you a conservation equation for the stress tensor. And you can do this in more generality. You take a primary here and you take some derivatives of the primary. So you build a descendant. And then you want to ask that the result is also primary. by requiring that you actually fix both the dimension of the primary and of this primary descendant. And so this dimension actually are actually known in any dimension, in any space-time dimension, just from representation theory. So this classification is actually already done. So in some sense, the problem is solved. I want also to mention that actually this particular combination of derivatives is, however, not known in any dimension for all these primary descendants. But however, this can be very easily done in 2D. That is the case that we care about. So in particular, we want to classify primary descendants in 2D CFT, and in particular, the ones with respect to global conformal symmetry. And okay, this is just known. It's like a very simple computation, and it amounts to take a primary and again ask that some descendants are also primary. And we find that there are 3 classes of such primary descendants that we organize with respect to the spin J prime of the primary descendant with respect to the spin of the primary. So you see here the primary descendant has greater spin, here smaller, and is equal spin in absolute value. And in particular, the third one is flipped. And here are the dimension when this descendant become primary. And here is exactly the form that they take. In particular, I want to mention that here there are 2 type 1 primary descendants that would correspond to these two descendants written here in this plane, where here is delta and here is J. And we see that on top there are always the primaries, and on the bottom their primary descendants. And it's important, yeah, we get 2 primary descendants of this first type. And okay, that's complete. It's completing the classification of primary descendants in all CFT2. I want also to mention that there are some shadow relations between these primary descendants, and you see that the primary descendants of type 1A and 1B are actually related by shadow. And also there's a funny fact that if you take an operator that has a primary descendant of type 2, then its shadow will have also the same primary descendant. And also the primary descendant of type 3 is related to the parent by shadow. And so that's completing everything, but what is the diamond then? So the diamond appears because actually every time we have a primary descendant of type 1, so these 2 guys, they themselves always have a primary descendant of type 2. And so we get this full shape, and we also think about this type 3 case as like a 0 area diamond. And so now we know exactly everything about this CFT2 case, but what we wanted to do actually is to study celestial CFT. So what can we say more? Well, in celestial CFT, we can say something extra because we know how to build the operators. So in particular, when we start with a Lagrangian that depends on some fields of some spin S, then we can build the operators just by some convolution of these fields with respect to some wave function. So it's the same thing that you do like for a Fourier transform, and you use plane waves. Here you use this nice primary wave functions, and with this primary wave function, we get back some operator here that actually transform like a primary. And so you see that in this picture, like all these operators are actually defined in terms of the wave function. So what we can do is to just classify the wave functions. But the wave functions are much simpler objects because they are just kinematical objects, and they are fixed by some nice simple requirements. So and indeed, so what we can do is like very schematically is this. We just take a wave function, we take some derivative, and we ask that this is going to be equal to another wave function that is a primary wave function. So this is a classification of primary descendant wave functions. And there are two different cases. One case is this one, where you get that the primary descendant here are actually zero wave functions. And so they are building the zero operator. And so this actually happens in the usual CFT also, that for the identity operator. The identity, if you take a derivative, is just the zero operator. So if you insert it in a correlation function, it's zero. While another case, and this is the case that should be related to this W infinity algebra. While the case that we studied the most is the case where the full diamond is non-zero, and so you get like 4 non-zero wave functions, and in this case you see that the left and the right corner would correspond to some conserved operator, and on the bottom, you would get there that you get some non-vanishing wave function that correspond to an operator that when you plug it inside the correlation function gives you just some contact terms. And this is indeed the definition of what happens from like a word identity. And on the top, indeed, there is something that is related to the dressing. I'll tell you something more in 1 second. So I just want to show again this this picture where you see all the diamonds for all the spins from 0 to 2, and so these are diamonds, all the wave function that you can build, and so all the operators that you can build with some fields of some spin S. And again, on the top there are the dressing, on left, right corner there are conserved operator, and on the bottom there are word identities. And there are many because you have the leading, subleading, etc. Word identities that would correspond to different soft theorems. And okay, let me just finish with a final slide where there is an example of a diamond in an actual CFT, because maybe some people could be a bit lost. So actually, if you study free boson theory, this diamond arises very naturally, and it's just this picture. So the action, of course, is just this one, and you have currents on the left and right corners that are just usually defined as some derivatives of the field phi, and on the bottom you would have the conservation equation that gives rise to the word identities. But you can, of course, since this is the shape of these currents, you see that it's the derivative of phi, so it's very natural to put phi on the top. The field phi itself is not typically considered as a primary of the theory. However, you can use it to build the vertex operators in this form. And the point is that vertex operators are what we think like as what does the same job as the dressing in some sense, because they change the charge of a vacuum state. And so this is indeed what is expected to the dressing. For an amplitude, you change the charge in order to make some non-vanishing amplitude. And so this is an example where the whole diamond appears, and hopefully this was helpful for somebody. So thank you.
So thanks, Emilio, thanks a lot. So now I think it's time for question for everybody, in particular maybe for Shamik and Emilio that didn't have any chance to get questions, but please just also to all the speakers of today, you can raise your hand or just unmute yourself as you prefer. Shubham, please.
Hi, yeah. I don't quite understand the diamond you show in the last slide. So as you commented, we typically don't include phi as a local operator in the unitary free boson CFT. Right? And in the free boson, J and J bar are actually the Virasoro primaries. And so why is it useful to group them together into a diamond?
Yeah,
I think I
indeed. I agree with you that the field phi, it's not itself usually considered as a primary, but it does. I mean, it has first one feature that actually that it doesn't make it like a nice primary, that the theory is actually invariant under the shift of phi. So it's already quite weird. The second weird feature is that it has a logarithmic two-point function. And so indeed, it does not quite transform like a primary, because you would want, since phi has dimension 0, it should just, it shouldn't scale. For example, if you scale the field phi by some parameter, you wouldn't imagine anything to scale. Like the other field that is usually considered a primary, that has dimension 0, is the identity. And indeed, the two-point function of the identity does not scale. But if you put together the fact that phi actually can be shifted, there's this shift of phi that is possible, and the fact that it's logarithmic two-point function, actually you see that it can transform like a primary up to, because when you shift the logarithm, you get the same logarithm plus a constant when you rescale it. But this constant can be reabsorbed by the shift of phi. And so in the end, the field phi itself actually does transform like a primary. And so it can, let's say that it makes sense to put it in this picture, because you can, I mean, it has the same property of the primary. And so it will satisfy the same algebra condition, for example.
So when you say free boson, do you have in mind the ordinary unitary compact free boson, or do you have in mind some logarithmic CFT?
No, it's the usual free boson, that where you have, I mean, you don't need to compactify it, but even
the usual free boson, precisely because the two-point function has a log, we don't usually include phi as an operator.
Indeed. So right. Indeed, what I'm saying is that it has the same properties as a primary operator, but, and so for example, when you do this classification of let's say based on representation theory, that classification will work for this field phi, because phi will transform like a primary. For example, if you act with, I mean, I'm saying a global primary. If you act with L1 or L bar 1 on phi, you annihilate the state defined by phi. Well, or let's say the commutation of L1 or L bar 1 with the field phi is 0. And so it in that sense, it transforms like a primary. And so when you study just this classification of primary operators, you can put it on the top. This doesn't mean that I want to put this state as in the spectrum of the theory. I'm not telling you that. I'm telling you that you can, that this state, this operator exists. You can study it. For example, it's completely fine to just study correlation function of phi, and that.
But it's not fine, right? Because it doesn't obey the cluster decomposition. It has a logarithmic divergence.
But still, you can compute. It. I mean, nobody tells you that. I mean, there's a very well mathematical way to define its correlation function. And you can compute any correlation function of any endpoint function of phi, and it's completely well defined just because it's free theory. So it's just big contractions. So that's actually completely fine, and you can do it. Then you may ask whether it's useful or not, and that I agree. But what I'm telling you here in this example is that if you are able to build the field phi, then you could exponentiate it. Imagine that you are given just a theory where you only know J and J bar, but you don't know the field phi. You don't know how to create the vertex operator. On the other hand, if you know a way to build the field phi, then you can exponentiate it and you can build a vertex operator, that is a good primary. And that is what I'm advocating here, not to use phi maybe in the spectrum, considering it as a new state in the spectrum, but that you can build it, you can build dressings would in this sense would be just vertex operator through phi.
I'm still completely lost. So in the physical unitary free boson CFT, phi is not an operator at all. Right? Phi is just not well defined. It has logarithmic 2-point function. We don't usually include it as an operator. Now we can put physics aside and we talk about representation theory of Virasoro algebra or of SL2C. If we're talking about unitary conformal multiplet, then there is no such a diamond starting from an operator with weight 0, 0. However, we can consider maybe more involved multiplet like logarithmic multiplet. Then there could be such a diamond. Maybe it's the last one that
we're also considering negative dimensions, right? So we're not.
That's right. So that's my last category.
Like
yeah.
So we're not talking about unitary conformal.
Right.
But the other
so
thing
that's why yeah. Sorry, go on.
The thing is that you don't care about unitary ones. I mean, it's there's no norm that you need to take for this classification. It's just commutation relations is just completely algebraic, and you don't care about it. The only thing that you care about it is the action of L1 and L bar 1 on the operator. And I'm telling you that the action of those one annihilate phi. You can compute it actually. I mean, you can do the example and you will see that you annihilate phi, and this is enough for what I care.
So we don't talk about norm in this multiplet, or do we?
In this case, I'm not doing any computation with norms, and so this does work. I'm just taking L1 acting on some descendant of a primary. And so I'm just commuting L1 with L-1 in practice. And so this doesn't do much beside the fact that in the end, L1 will act on the primary itself, and you want L1 to kill it. That's the only thing that you are asked to do.
And does L0 diagonalize your primary?
L0, well, L0 still gives you the dimension of the operator, which in this case would be 0. So yes.
So L0 is diagonalized.
Yeah.
Okay.
So I don't think it's correct to say that it's a logarithmic multiplet.
Okay,
I don't think so.
Okay.
I mean, yes, indeed. You don't have any Jordan structure for L0, so that's fine. I agree with you that I would not argue that you should include phi in the spectrum.
I don't understand that. If the 2-point function is going like a log, then by definition, then it's going to shift when it's not an L0 eigenvalue. It's not.
Yeah. So the point is that if you act with L0, you will see that it gives you 0. I agree with you that if you scale the field, it looks like there's something very fishy going on because there's a constant term appearing. But actually, you should remember that the field phi is defined up to a constant. And so that's the catch that makes everything actually meaningful. I was also very confused about that, but it does work if you act with the Virasoro L1, well, the global part of the Virasoro algebra on phi. I mean, I did the exercise. You can do it. It works. It transforms like it should any other primary field. So, well, global primary. I promise.
Are the things at the top and the bottom of the diamond shadows of one another?
No.
For part 3, for the type 3 ones.
Yeah, just for type 3, yes. But when you have this full diamond, no.
But if you're saying that phi is only defined up to an additive constant, then how can you define the exponential operator? In that case, the exponential operator would not be defined.
Well, indeed, that's the point that you should actually. It's really the point of the vertex operators. When you define the vertex operator, they carry a charge because they are charged with respect to this shift. And indeed, you can use them to charge the vacuum. So if you, let's say that you define it in some way, given some way of definition of phi, then you act with this vertex operator on the vacuum, and it will charge the vacuum by the coefficient in the exponent in front of phi in practice.
So are you saying the shift symmetry is a gauge symmetry, or is it a physical symmetry? Because if it's a gauge symmetry, then you're not allowed to have charged vertex operators.
No, it's not the gauge. I mean, this is just a theory with some global U1.
No, it is a gauge symmetry. It's exactly the large gauge transformations in the example.
I mean, it depends on the language that you want to say. If you just study a CFT2, that is a free boson, it's
no, but this is not the ordinary free boson.
Right, that's what I'm trying to understand, because
why not?
Point
it's
still
not
holds. If it's a physical symmetry, then the operator phi is not well defined because of a logarithmic singularity.
Yeah.
No.
But if it's a gauge symmetry, then the exponential operator is not well defined.
In an ordinary unitary free boson, phi is not an
it's
operator.
That one.
Yes.
And there is no such a diamond in the ordinary unitary free boson.
I'm
I
sorry.
believe you're talking about some other theories.
No, you are actually. I'm not talking about another theory. I'm talking about the usual free boson. The usual free boson.
But you never asserted
there is a field phi in the Lagrangian. Are you?
No, but that's not an operator on the Hilbert space. That's not an operator.
Nobody
that
told you that it's an operator on the Hilbert space. I never said that. I'm saying that there you have some field in the Lagrangian that, for example, you can expand in modes, as it's written in any books from I don't know, Di Francesco to any string theory book, and you expand it in modes. And then you can, for example, define a derivative of phi, and you see that is actually a very nice operator that is that would be actually a Virasoro primary. I agree. Then the other thing that you can do is to take the exponential of phi and define a vertex operator as I mean, I'm not saying anything weird. It's like
no, but then I'm not understanding the celestial diamond that you have. I thought the diamond was a diamond of operators that act on your
exponential is fine. The derivative is also fine, but phi itself is not fine.
I agree. I'm
also
telling
the
you
one
that
at the bottom
phi is not. Sorry.
Yeah.
No. It's actually very important. And the fact that so we draw these diamonds, and the most important thing is that so what is at the left and right corner and what is at the bottom. Well, left and right corner are actual operator. At the bottom are just derivatives that gives conservation equations. So this is kind of 0 up to contact terms. So it's not quite an operator, but it's fine. What is up on the top? I'm not saying that it's an operator in the Hilbert space. I'm just telling you that what it's at the top, it can be useful to build some other operators that are the ones that are responsible for the dressing. And this would be the case for these vertex operators. So I'm not saying that phi should be considered as an operator in the spectrum, but that you can use phi to build the exponential of phi. That's my whole point.
So
I don't know if it's
invariant meaning for that diamond.
Yeah.
Sorry?
Is there any invariant meaning for that diamond?
So the point is that if you want if you take the left and right corner, they are the right primaries.
Certainly.
Okay. The top is something that indeed could have been written in any book of let's say even in different shapes, you can write that phi is such that the phi is equal to something. And so you can put it formally at the top of a diamond, okay?
No, so for instance,
of course,
I can describe this free boson theory without ever talking about phi. I can describe it by simply listing all the operators. I will list J, J bar, and I will list exponential operators. Now, in this description of the free boson theory, where is your celestial diamond? There's no phi anywhere. I only have exponential operators. I only have J and J bar.
I agree with you, but imagine that you don't have all the operators. Imagine that you are just given the phi and the bar phi. And you want to build the vertex operators. How do you do that?
Well, I think the modern way of thinking about CFT is that there's a list of local operators.
Yeah,
It may or may not come with the Lagrangian.
I agree with you, but we are in a
consistency.
special kind of theory, no? It's a special kind of theory where you should find your operators. The operators are not known, and you want to find them, and there's a prescription to find them starting from some wave function. And I'm telling you that there's a prescription to find this operator that I think will be good operator after exponentiation.
Well, but I think in the case of super translations, the thing at the top is not of dimension 0. It would be dimension -1/2, -1/2, and maybe that's a little less confusing. In that case, can you find an explicit wave function for that? A bulk wave function?
You could write them formally down, yeah.
Yeah,
you can write it down.
Actually,
and
I
for
should leave
example,
my collaborators.
No,
in memory diamond, you find the gravitational shock wave, the Affenberg axial shock wave, has dimension -1, J = 0, which corresponds to the weights HH bar that you. So that's a solution. It's even a finite background, and it transforms as a conformal primary with delta = -1 and J = 0.
Right, and we could also, it's related by the light transform to the usual one, right? Yeah,
It ends
that's
up
what
being,
you're
yeah.
saying. Yeah. So they can be pretty explicitly described. This log business doesn't come up for super translations because
you see it literally in the correlators, right? Like you see that in your 2-point correlators for your C in the paper with Mina and I think
right.
also
Right. Oh, right. There were logs there.
So basically, I mean, the point of view that Emilio was saying is exactly what I would say is like, we aren't handed these. I mean, you can do the route that Kevin and Jacob do, which is start from the full gravitational theory and then try to find effective modes for like the goldstones. But if you wanted to kind of excavate things from the soft theorems, this is how you would build it up and identify where you need to augment the spectrum. So that's the point of view. And yeah.
Maybe Thomas, a question was raised hands since long time.
Yes. Oh yeah, okay. Emilio and Shamik, thank you much for a wonderful introduction. My comments are connected more to Shamik, and I have also some questions. Okay, so let me start because we are talking about Bootstrap. Your introduction to Bootstrap. Now, Bootstrap is, is a very powerful technique for constructing things you do not know. Yes, which means like people construct correlation functions by using self-consistent conditions. However, in our case, for 4-point functions, we have what we have. Okay, so what we use Bootstrap, for example, in our recent work, just to check as a self-consistent condition, yes? So we have a crossing equation, one channel and another channel, okay. And so there's an interesting thing that actually this paper appeared this last week. At that time, somehow I was not aware of your work on those equations, which you think that may be useful for Bootstrap. Okay. Okay, so now we noticed it only last weekend, and I think there is a Ben. Is Ben my student? Benzu, are you there?
Hi, yeah.
Okay, maybe he can comment about that. Okay, about your equations.
Yeah, hi. Can you hear me?
Yeah.
Okay, yeah. Yeah, so we realized that our 4-point single value amplitude in our paper actually satisfy the differential equation in Sharma's paper and Bonomich's paper. So, but in our case, we only consider the lambda 1 equals to 0 limit. So actually, what we can only check is we cannot check all the differential equation. We can only check one differential equation, which is true. But if we can get the general lambda 1 case, the general expression for general lambda 1, and we might be able to check all the differential equation in your paper.
Yeah, that brings me to the question the question for Shamik. What is really the physical content of your equation? Because is it like the Mellin amplitude, the original Mellin amplitude, does it satisfy this equation or not? And what is the physical content of it?
We can't hear you.
Okay, I was just unmuted. Well, so one way to think about so at the end of the day, so if you solve them, so what you will get is something that we all already know. So from that particular point of view, I think, well, I mean, it's not very useful in that sense. But the thing is that the reason we were interested in doing that was to basically show that you can solve these AS matrices in this particular spatial case using just the asymptotic symmetries, and that in some sense it tells you that, well, I mean, there is some kind of, perhaps, I mean, at least at tree level, there is some kind of holographic description for the flat space scattering, and yeah, I mean, that was the And the second thing I would like to point out is that the standard S matrix bootstrap, that works best if you don't have massless fields, right? So that we know. So, but these things, this approach of spatial holography, so that basically gives a way of doing the way of bootstrapping the massless S matrix also. So that was one of our well, I mean, the reason that we did that actually. So yeah, I mean, at this point.
No, I was just asking. I was just curious. No, it's maybe misunderstood my question. I was.
No.
My question was whether there's a simple question: whether the Mellin, the 4-point MHV, gluon MHV, it does. So in other words, so we see now also the single valued one satisfies. So yeah, okay. So that's why I was wondering what is behind it. What is really the content? Is it well, like for example, for OPs, like Andy was using translational variants. Yes. So what is behind those equations? That's what I'm curious about.
Well, those equations, they come from the decoupling of the null states, right? So you have this SL2C bar algebra and the super translations. And well, you are talking about the gluons.
Yeah, I'm talking about gluons.
Oh,
so I'm wondering what
oh.
null states you are talking about.
Yeah, so it is the null state of the ACU, the standard, the ACUN current algebra, and you also have the subleading soft symmetry. So you have to take both of them actually. So then you can get those. So these are the null states of them. So the ACUN current algebra and the subleading soft gluon. Yeah.
Are these the same as the states at the bottom of the celestial diamond?
Are these the states? Well, so Sabrina and Emilio was talking about. So they talked about the SL2C. But these are the local, like these are the Caxmudi. So that's the difference actually. So they talked about the global, like the global algebra in the sense, the SL2C, and I like the.
No, but there would be a null state at the bottom of the celestial diamond for the Caxmudi algebra or whatever. So
yeah. I think if you extend that, yeah, precise. Yeah, I think so. Yeah, right. So if you extend it to that, include this Caxmudi structure, then yeah, that's what you will get actually. Yeah.
So the diamonds that Sabrina and Emilio focused on mostly were the ones where you had actual primary descendants at the bottom that were still delta functions inside correlators. And those, for the case of gluons, you have the leading gluon, which is a non-degenerate diamond. For the subleading gluon, you get this degenerate diamond where the top and the bottom are related by shadow. And then you get a whole tower of null states if you go to more and more negative dimension, just because of the fact that you're taking derivatives more than what the exponent of Q dot X is. And so you get this tower as well, but
they only talk about the global symmetries, right? Yeah. So in this case, actually, you also have to talk about the local one. So that's an interesting point, like how to extend all these structures to the local algebra, like the local symmetry algebra. So that should be done actually with norms and all these things. I mean, yeah. So yeah, I mean, if that can be done, I mean, that will be, yeah. So that will also be very exciting, I think, because that will be very powerful. Yeah.
More questions? Andy?
For Shamik. So in your last slide,
right,
you said that the bootstrap problem was already solved for CCFT because they're all values of delta, but I'm wondering if there's no problem of determining the spectrum we have every.
Yeah, so what I meant was that it's a half of the bootstrap is kind of solved in the sense that we don't like the scaling dimensions are not like they are not fixed numbers, so it's up to us like which delta we choose. So in that sense,
Well, I'm not sure. Is it up to? So I'm wondering if we might think about it in the following way. So, or if you think this is the right analogy. So, if you write down the Lagrangian for Liouville theory in 2 dimensions,
yeah,
you can take the exponential of the Liouville boson and you can write down an operator of every dimension, of any complex dimension. But we wouldn't say that Liouville theory has an operator of every complex dimension.
That is true.
Because those operators they're not linearly independent.
Yeah.
And precisely what the bootstrap program did over a 20-year period with Liouville, and it was a surprisingly difficult problem, which I guess the Zemlyanikov solved, is to show that the dimensions of allowed in Liouville theory are some semi-infinite discrete set. Or there's a continuum, and then some other theories, there's a continuum and a discretium. So it looks, from that point of view, it looks very similar to the bootstrap problem that has been solved in some conformal theories. And we know that these deltas are not, the operators created by different deltas are not all independent. And the question of exactly what deltas we should take is indeed a highly non-trivial question. You know,
yeah. Is it related also to the fact that you are talking only about global blocks, but you may have something more related by Virasoro?
Yeah, we have to solve that too, right?
Yeah. So in this case, if I just think about this delta equal to 1 plus I lambda type of states actually. So those are there, like so that lambda is not fixed. So that I think, so that you agree with that, like we can take
yeah, but I think it's pretty clear that that's not, I mean, that's
not the
that set of states is not even mapped to itself under translations, right?
Yeah,
because
that is true, because yeah, it will increase delta by 1. Yeah, I mean,
yeah, so maybe the integers.
But so I think Sabrina and then Andrea, so they actually, if I remember, so they showed that those modes with delta shifted by 1, I think those can somehow be written as integral of the modes with delta equal to just 1 plus I lambda. Is that true? Something like that?
So sorry, say it again.
No, I'm saying that this when you shift delta by delta equal to 1 plus I lambda to delta plus 1, then you get, right? And can that be written as an integral of the modes where delta is still of the form 1 plus
the principal series?
Yeah.
Yeah. So that was the point of the paper with Laura and or one of the points with Laura and Sabrina, where we showed that you can write off principal series wave functions or operators in terms of integrals on the principal series. Yeah.
Does that include operators at every integer?
Any complex delta in principle.
And then
yeah, but there is one thing which is different here, that I think that everybody will agree now that there must be also primaries, which are, for example, in celestial Young mills, which are not an adjoint, yes, which are in different representations. And I don't know how to reach that. That's clear that you won't reach them this way. I'm just curious, how can you reach possibly primaries which are in a different representation of the gauge group? Okay, so there must be some relation.
Yeah, even worse, in our paper, we had started with massless scalars, and the conformal block decomposition had massive,
yeah,
even with the contact interaction, they were implicitly massive. Yeah.
So that brings actually to the question, which is another question, which is, what is if you even have suppose that wherever you take and you have conformal block decomposition in 2 dimensions, what is the physical interpretation in 4 dimensions? Yes, whether these states have anything to do 4-dimensional physics or just completely 2-dimensional.
Well, couldn't it be a bound state at threshold of 2 gluons?
Well, that would be great.
Well, that's what you're saying. I mean, there's no reason that shouldn't happen.
Okay, so we say that are you saying that, for example, you take SU2 singlet, which is dimension 2 plus I lambda, is it somehow, can you see it from as some four-dimensional physical state, or is just some partial wave decomposition of the amplitude? You understand what I'm saying?
Well, maybe you can see it in the operator product expansion.
Yeah, okay, so we have an operator product expansion, yeah, but now whether all operators which appear on the operator product expansion, which are not in principal series, but they out of this 1 plus I lambda, whether they correspond to some physical states or some physical phenomenon in 4 dimension. You understand my question?
Well, yeah, we have a dictionary. We can always go back and forth, right? We can, if we understood the problem of collinear singularities carefully in the 4-dimensional operator product expansion, we could, in principle, understand it that way. It's just a very awkward.
Yeah, well, if you are talking about then you are going very far, because then if you have operator expansion of gluons and you find singlets and you find different representations of the gauge group, then this is something really dramatic, yes, because you are talking about the spectrum of Young-Mills, yes. Okay.
You wrote the paper, Tom.
Actually, on that note, Tom, can I ask you, maybe you mentioned this during your talk, but at the end of your talk, there was a discussion about what the momentum space version of your single valued Mellin amplitudes is. If you just did the inverse Mellin transform, is there an obstruction? Can you, what's the?
It's question
to you. Yeah.
Oh yeah, okay, but could you repeat
about doing the inverse Mellin of the single valued amplitude that you have given a prescription for? So there was the question, what is the momentum space interpretation of that?
Oh well, of this, what is the momentum space interpretation of this final amplitude? Okay, exactly. Which you get by taking inverse. Well, that's the question. I can only, you may ask whether it's an amplitude at all, and that was related to, I think, Atul's question before.
Yes. Mm-hmm.
And what I'm saying that on the, you see, it's again, this amplitude is defined on a whole complex plane of Z, yes, of the cross ratio. Mm-hmm. But of course, now that Z, in physical amplitudes has to be real, yes. So I believe that on the real line, it should be related to physical amplitude. So the single value amplitude should be extension, should be self-consistent extension of the amplitude beyond momentum conservation. However, when your Z is equal to Z bar, you find a physical amplitude, which you should be able to construct by some other methods. Now, the evidence, maybe I repeated again this argument, which when I was answering Atul's question, that you can go, like for example, normally in celestial, when you construct celestial, you take Mellin, for example, Mellin transform, you can either start from MHV or MHV bar. Yes, the two, which is one is with the wedge brackets and one with the square brackets. Yes. Now, the relation, the fact that MHV is the same physical amplitude as MHV bar is due to momentum conservation. You can go from one representation to other by using momentum conservation. Yes, the two. This is one. This is a representation of the same physical amplitude. Now, you can do the same thing what we did. And instead of going through the shadow loop, yes, this shadow detour, as we call it, instead of starting from MHV, you can start from MHV bar, yes? Then the answer is obvious what you will get. You will get not the amplitude that we have the single value, but it's complex conjugate, yes? So now the two should be equal. They're equal only when Z is real. So that's make me think, personally, well, that's what we think, that it really represents some physical amplitude on the real line. Okay, so yeah, so that's how it is related to some physical amplitude. Yeah.
But you don't have a momentum eigenbasis interpretation.
Of course, in other words, you will have to think about it as you extend beyond, you violate momentum conservation in some way, okay? And then, but when you bring to when you go to the this constraint situation, when you have the momentum conserving, when you have the points that cross ratio is actually real, then it should give you the physical amplitude. Yeah, so that's right. So in other words, the momentum conservation shows up. When you have momentum conservation, you get the amplitude. But we have something which is defined also away from the real axis.
Monica?
Yeah, so to follow up on that, right, essentially you're saying that you have a particular way, if I understand correctly, of representing the amplitude off shell, right? So,
I'm not sure if it's off shell. Again, I cannot really make a really precise comment because I really don't know how to produce this amplitude. Off shell, when you think off shell, you think about configuration, which you go off shell, but still momentum is conserved, yes? So I don't know whether, I think it's more somehow, yeah. I don't know exactly, I cannot, at that point, I cannot give you precise connection between the single value amplitude, how it fits into this whole context of momentum conservation.
But can you at least do maybe what Andrea suggested, where you inverse Mellin transform it and try and write it in terms of momentum? Like, is that even, and see what it looks?
Oh yeah, I think that there may be a way of doing, there may be, I think that the natural place, looking at the final result, which is just the way I think about it, looks like an iris super amplitude, okay? An iris super amplitude just fits very well into Witten twisters, yes? It comes out naturally. So I think that it should be somehow a relation. You should be able to get this single value amplitude by this type of a construction, which would have to, in some way, by momentum conservation or something like that. But it is, you know, at that time, I'm, you know, I cannot, I wish I could tell you something more precise, but yeah.
What I was worried about is that, so you could do this computation, right? You do an inverse Mellin on all the external legs, but is there an issue with the well-definedness of the inverse transform or convergence issues? And that was my question. Whether there's an obstruction to just brute force doing the inverse Mellin transform and seeing what you get.
Oh, no. What the construction was that we started from Mellin, and then we went through this loop, which means that we get the only thing that we use is a requirement that it's single value. We just want to get rid of this complex spin, okay, which is bad on complex plane. And we use all tools that you use from a Euclidean CFT. And then, at the end, so we started from the shadow, and we end up on the shadow of something, which was now supplemented by these terms, which make it single value. This is Dotsenko. So in other words, we use this at some point, and on this loop, we are able to produce Dotsenko-Fatiev representation of this correlator, and then we can write it as a shadow of something. And what I'm saying that this as a shadow of some 4-point function. And this is what we call this 4-point single value amplitude.
Yeah, and then understand that once you go to the Mellin amplitude and then you do your shadows and so on and so forth, but then
I don't think there is a way, but yeah, I don't think there is a way. Yeah, I understand what you're saying. I mean, there's no, I think there is, you are talking about the running through the river of crocodiles, yes, which is, I don't think there is a shortcut from there. You cannot get from, by some modification of Mellin or doing some Mellin to get the single value. It's just too, this whole thing is, this detour is quite sophisticated, I can tell you. I don't think that you can, but who knows, yes, who knows? Yeah, that Mellin, in other words, modifying Mellin or starting in a different way with Mellin when you can get there, or spending some prescription, who knows? But I think it's very unlikely because it's, this whole construction is really this whole construction, I can tell you, I mean, the miracle is at each step. Yes, the fact that you by doing, starting from this melon, you get the right OPs, I mean, with the right coefficients. And then in addition, when you go to Dotsenko, you're able to write the shadow of something. I mean, what can I say? I mean, that's very strong evidence that it leads to something which makes sense. Even if you cannot write it as a melon in a simple way.
Andy?
Yeah, this is for Shamik and Tom. So you have these null state conditions, equations, for the amplitudes that I think they were melon amplitudes.
Yeah. Right.
And then Tom took the melon amplitudes equations and found that they were obeyed by the shadow of the 4-point function with one shadow, right?
No, we went back to the amplitude.
You went back to the amplitude.
Yeah, we inverted the shadow. The final product is the amplitude. But this happens, then one should be careful. This happens in the limit when the shadow is soft. So, okay, so I cannot, this whole, the amplitude which I have is when one of particles is soft.
I see. So you weren't finding that a generic 4-point amplitude obeyed the Shamik's equations with the shadow.
Because we don't have it. We don't have it yet. Yeah.
It might, but we don't know. You don't know. Or
I don't know. I don't know.
Yeah, perhaps it won't actually, because I think because the OP will change. Like if I the gluon OP,
yes,
if I make one of the gluon the
yes,
and then the OP will change, and then this not state I think will be gone. I mean, if you just
actually you see that it's not we didn't write it, but it is sort of obvious that
because
actually the OP of two gluons now will be the usual OP that we know, but it will involve a shadow too.
Yeah. So
okay, so that is already, we see that. We didn't, we want to, when we have the full amplitude for we will go away from the sublimit. That will become, we already see that it's happening. Yes, that's something which you couldn't.
So if you do go to Etole's light transform, the OPEs still have this beta function in it, which would seem to lead to the same. So you might think that the null state condition
will exist.
You might think it still works there. I don't know. I don't know when it's supposed to work and when it doesn't.
Yeah, the point is that the so the subleading terms in the OP, how do they look like in the? I mean, if you have the
subleading terms involve already. So anyway, the conformal block spectrum is very simple. It's one is n plus I lambda. So integers plus the usual stuff like n principal series. But now when you're starting from, go beyond the lowest one, which is m equal 2, then you have, and then you can do it explicitly as U2. Okay, so you have a singlets, you have a triplets, and you have quintuplets. If I just can 0, 1, and 2, which appear on OPs with various beta functions, we can do many things about. For example, you can check where these conditions, these conditions, which are the translational super translations, do how they act, and you can check it. Then all these OPs have beta functions which are consistent with this super translations.
Yeah.
Okay, so there are many other an OP. If you take two gluons, first of all you will get the gluons. You will get shadows, and then you have you go further, and you get really lots of really weird stuff. But still, dimensions are just m plus I lambda.
Yeah. Yeah.
Well, the fact that you will have the states which are not in a joint is you cannot avoid it. I mean, just it's common sense, yes, because you are colliding to why it should be any can produce anything, yes.
Atul?
Yeah, I was also wondering how would Shamik's differential equations look in a light transformed or shadow transformed basis? Is there some easy way to translate them? Maybe do you have to for that? Do you have to compute the shadow OPE first, or can you like do some shortcut?
Yeah, I don't know. I mean, if you have the shadow transformation, then how it works?
Shadow, light, or whichever.
Some things will change. For example, the OPE of the J's, the currents that we have. So shadow, yeah, but yeah, it just depends on that whether the null state will be there or not, because it is like the J phi. So that should basically, I mean, how these transforms, because the existence of the null state, that of course, like, I mean, it is best way to see this is just doing it algebraically. Like we know, I mean, which modes will annihilate that state, and then. So I think, yeah, it is just basically the J phi. So whether phi is shadow or not, so that, yeah, I have not really, well,
That's
yeah,
okay.
but I think that can be done, yeah.
I also had a question for Thomas. So in your calculations, you checked that the leading OPE of the beta of I lambda 3, I lambda 4, that works out. And you also had these other conformal primaries with m plus I lambda weights. But if you like take a particular conformal primary, could you also try to do subleading expansion and check the OPE coefficients of, say, Katz-Moody or super translation descendants, because that's, or yeah, Katz-Moody in the Engels case, because at some point your single valued amplitude OPE expansion has to be different from the original non-single valued celestial amplitude. So can we see this difference in the OPE coefficients of the descendants, maybe, if not at the leading order beta function?
But you can, I think that you can see it or the leading order, not the leading order. You can see at the primary level. Yes, descendants. I'm not. Yeah, descendants. You pay much attention to them because you see that we have primaries which are entered. We have all blocked the compositional coefficients, so we know. Essentially, we know completely the conformal. We know all the spectrum of conformal blocks. Yes. So the only thing that you can do in this case, okay, so the bootstrap, okay, look at the bootstrap, okay, use the crossing equations, okay. So you look at the OP in one channel, and then you compute it with the OP at that level, yes, at that next leading level in another channel, and of course you can construct self-consistent solution. I'm just wondering whether there are some more general. But this is case-by-case basis. We did. I'm wondering. I don't know much at that level of CFT, whether there are techniques which will allow checking these bootstrap. It will be interesting to try to apply these bootstrap equations, which would encompass actually all orders of the operator product expansion. I simply don't know how to do that. But on a case-by-case basis, we can pick up several primaries, which are, for example, isospin 2, yes? And I have the all OPs, and then I can reconstruct the from the 4-point function, I reconstruct the whole factorization chain and reconstruct all OP coefficients. Yeah. But does that answer your question, or?
Just a comment. Just to comment on that, you can't really say what the OPE is until you have you know what a complete basis is, right? So, but I mean, I think you've given it. I think you've made a compelling case that there must be these things in products of the adjoint. But if you were doing the scattering, somebody told you this was a complete basis, and you were scattering those states and you found these things in there, then that is a computation of the OPE. Extracting the OPE out of the 4-point function.
Yeah. Well, yeah, so yeah, okay, so we need that is true. They go higher levels, then it's not. When you have just more of primaries, that's true. We go to higher levels, then you need to choose a base and so on. Yes, I agree with that. Yes.
There is Alok with a raised hand.
Hi, can you hear me?
Yes.
Yeah, I had a question for Thomas actually. So Thomas, you had this in the 4-point amplitude, it was one Park-Taylor and rest with a conformal factor, right? In the Young-Mills case.
Yes.
So I was wondering if this could come from double copying bi-adjoint scalar. I mean, have you looked at it that, it was like in CHY, the bi-adjoint scalar is like 2 Park-Taylors and we replace one of the colors factors with a Pfaffian to get the Young-Mills amplitude. Is it possible that you have the single valued amplitude for bi-adjoint scalar, which after double copy gives you the Young-Mills single valued amplitude that
I'm a little bit confused because you are talking essentially about gravitation amplitudes, a double copy, yes? So
no, just to obtain the Young-Mills from the bi-adjoint scalar. So you could have, you can double copy bi-adjoint scalar to get Young-Mills, right? You can go the other way. Yeah. So I was wondering if the
I didn't think much about. Yeah, that's possible.
So in principle, it is possible that there could be a single valued amplitude for bi-adjoint scalar, which after double copying gives you the Young-Mills that you
could be.
You haven't looked at it.
I don't know.
Okay.
More questions? Also for, I don't know, with Anna, Sabrina. I think we don't have Miguel any longer, but Tristan?
Yeah, actually, sorry. So my question is for Shamik, and I guess I'm curious if these equations that you have for, say, in the gluon case, is there new content, or are they equivalent to known relations? So if I take MHV tree-level gluon amplitudes, right? I know I've got U1 decoupling, Cloyce-Klauf, and I've got BCJ relations, between the different amplitudes. And I was wondering, can you tell if these differential equations are equivalent to the set of known relations, or whether they imply some new set of relations?
Well, I don't know. I mean,
so I guess one way,
because the way we got them, so that looks like very well. I mean, you have this Cax-Moody algebras, and it just comes from there.
No, I understand.
Now, apparently, is there any way to see that how the things that you were talking about, like BCG, and they could be how
so they relate amplitudes to each other. So they correspond to relationships between amplitudes. And so I guess the same thing would be, the question would be, these differential equations, do they correspond to relationships between amplitudes, and are they the same relations that we already know?
Yeah.
So as an example, I recall in momentum space, you could make some sort of, like these KZ equations, right?
It looks like that actually. Yeah.
Yeah, exactly. But you could without doing the Mellon transform, you could write down KZ equations for MHV amplitudes.
Yeah, but the thing is that I think you.
No, but just finish. I was going to say that those relations, at least at low points, were equivalent to BCJ.
Yeah. Oh, okay. I see what you're saying actually. Yeah. So I think if you go to the momentum space, then you can write this KZ, but it is not exactly KZ because you have a term which comes from the subleading soft gluon, like subleading soft gluon theorem, and that is a change actually. So it is not exactly KZ. So that is
no, exactly. So I'm curious if there is. Okay, so I guess the answer is you haven't checked, and yeah, I mean, I wonder if there is a.
Yeah, let me make a comment about.
Can I? Oh, sorry.
Yeah.
Okay. So you can't have more. I mean, the MHV amplitudes there's enough relations there to completely determine them. So
yeah,
impossible logically to add an unknown, independent relationship to the MHV amplitude. I think what's different about the way you formulated it is that it comes from the soft theorem, and so it's very plausible that there are implications for the exact theory.
Yeah.
Can I say something? Yeah. Sorry. Yeah. Sorry. So this is actually based on Tristan's old work, right, where they look at this. So one difference I think is that was for stripped amplitudes. So the delta function was not included, and the point is that even though I think Tristan checked it for lower point amplitudes, I think you can show that for the stripped amplitudes, if you use soft exactness, actually you can show it for endpoint amplitude for the MHV.
So I guess I didn't actually mean to say that I was just trying to make the point of you can have relations that are equivalent to known relations. I didn't mean to say that these were the same at all. So
I think no, actually I'm trying to say they are the same. I mean, in the sense that
they are the same.
Yeah, they are the same, except that the ones that you work with are for stripped amplitudes. But if you include the the momentum conserving delta function, then you have to expand the delta function. Then of course you get the expansion of the delta function. But that's like that's a trivial content of the expansion. So the non-trivial one that you have. I think that's the same.
I see.
Yeah.
Okay.
I
see. Thank you.
That the differential operator doesn't act on delta when you apply.
I mean, in the MHV, that's the only one because the MHV amplitudes are soft exact, right? So if you look at the stripped amplitude, then the Weinberg soft factor is all you have for the stripped amplitude for the gluon amplitude. So the only way you get the subleading contribution is if you include the delta. Otherwise, you don't have any subleading contribution in the MHV for the tree level. For the stripped amplitude.
What do you mean by stripped?
No momentum conserving delta function, just the stripped amplitude itself without the momentum conserving delta function.
Oh, that.
Yeah, that is soft exact. That is soft exact. That's soft exact.
So it's not what we call this. So it's not this delta. So this delta of Z minus Z bar, you have to just throw it away like that?
No. So if you include that, then of course soft expansion includes the expansion of the delta. But that's in some sense I would say like it's a trivial part of the soft expansion. The non-trivial part which comes from the Weinberg soft factor. I mean, there's nothing more in the MHV than that. There's no Kachazo-Strominger type soft factor for the stripped amplitude.
Yeah, I think the point is that the point I mentioned in my slide is that like it is hard to say something completely new about the MHV amplitudes, but the reason the reason we did this thing was that this was basically done from the point of view of the dual conformal theory. So that's basically the reason like why this thing was done actually. Yeah.
If anyone from the Brown group is here, I think they
have something interesting on this.
They recognize your differential equation as some kind of BCFW shift.
It actually basically tells that how the amplitude will change if you make a BCFW.
Right. I'm sorry, I'm on the road, but maybe Li Cheng and Yang Rui can explain. Yeah, it's very simple. It's just it corresponds to BCFW shift. There's nothing from the point of view of amplitudes. It's, yeah, we wrote a paper and it's a very simple differential operator which corresponds to BCFW shift, and that's what these equations are in the momentum space. So, but there's Yang Rui and Li Cheng. I maybe they can comment more because I'm on the road.
Tom, you're muted.
Tom, what you're saying looks interesting, but we can't hear you.
Yeah, what I'm saying, but then on the other hand, well, maybe related to BCFW, which is related to like MHV and so on, as you know, but the single valued amplitude that we have doesn't seem to have any relation to BCFW or to anything. So it cannot be an accident that there must be something deeper in your equation, Shamik. That's what I'm saying. There's something more related to the null states, to more, it's not just like BCFW shift or whatever. It's something which is CFT of CFT nature.
Yeah, so that's how we got those things. Actually, it is a decoupling of the states, these states of the year. So that is basically, yeah. So that was essentially the main point, that these things decouple and then you can solve these S matrices. But yeah, at the end of the day, of course, we know what we'll get if we solve this. Yeah. So that is.
Yeah, it's also related to the fact that, like, for example, you have when we see that, then when you follow, you also pointed out the minimal models. And yes, there is a relation is that minimal models, you have just two blocks, you have block and shadow block, and it's related, but here we have it only on the anti-holomorphic part. But that is somehow not, so that may be related to the fact, like in minimal models, exactly, defined that you have null states, yes?
Yeah.
So
yeah.
Here you have a part of it, which is anti-holomorphic part, and that somehow makes it happen, and that limit the soft shadow limit. But I think there's much more to it. It's more CFT.
More questions, comments?
So I have a yeah, I think Andy or anybody can take this. So is there anything known about the dual of like some string? I mean, string theory background, the dual of that, like the holographic dual of that in class, like. Is there any thoughts on that?
Well, yeah, I mean, I think people are thinking about it, and I think it's something that I mean, I guess Thomas has written some papers about what the string theory, the only examples that we have of consistent amplitudes. And maybe, some of us here have been talking about trying to find a dual of the n equals 2 string, though I'm not sure how well understood the n equals 2 string is. But I think that that's a very fertile place to strengthen the connection with string theory is certainly, I think, a really important direction.
And the other idea that where the string world sheet becomes the celestial sphere, I mean, along that line, I think, I mean, was there any progress on that? I mean,
yeah, I think that should be true. And another thing that's really, I mean, another thing that, you know, this whole business that, you know, people have been talking about the conformal block expansion and, you know, and writing four-dimensional scattering amplitudes and then decomposing them either in the S channel or the T channel or the U channel, not the S channel plus the T channel plus the U channel, which was what we do in Feynman diagrams. Mm-hmm. So of course, that is the starting point of fundamental string theory, that you want to construct amplitudes using string, using world sheet string that automatically gives you S or T or U, not S and T and U. You know, the fact that the sum over S was the sum over T was, you know, that was the original, that was the beginning of string theory. And so now somehow we've magically used space-time symmetries to conclude that all scattering amplitudes in quantum gravity, in a consistent theory of quantum gravity, must have this property, though we don't really understand it. There's still a lot of confusion about this conformal block expansion, and but it seems like they must have this property. So it really seems like we're getting pushed into string theory in some form or another. And then there were also some nice papers from the group in Italy relating the soft, I think they were driving the soft theorems from the world sheet point of view, which is getting close to relating operator product expansions on the world sheet to those on the celestial sphere. I think there should be some, I think there's some nice connections waiting to be made there.
Right. Thanks. Yeah.
More questions?
I have a question. It's kind of a general question about conformal block decomposition. So in ordinary CFT, if I have a 4-point function, there are two closely related decomposition that people discuss. The first one is to decompose the 4-point function onto the conformal blocks. It's typically a discrete sum, and each term has scaling, corresponds to an intermediate primary operator with positive scaling dimension and integer spin. And the coefficients in the case of identical scalars have to be positive. And that's where all the bootstrap program comes from. And another decomposition is the conformal partial wave decomposition. And that one is in a way more trivial because it's just a statement of completeness. We can just expand any function, not necessarily related to 4-point function. We just can expand any function on this complete set of conformal partial waves. And they are typically labeled by integer spin, but scaling dimension on the principal series. And I think both expansions have featured in the discussion of celestial sphere, especially, for example, into the Anna Maria's talk. I think both expansions have appeared. I just have a general question. Which one of the two is more relevant for the celestial sphere? In ordinary CFT, it's definitely the conformal block decomposition because we see the physical primary operator, the physical states in that decomposition. But for celestial sphere, we have this long discussion about whether the operators live on the principal series or elsewhere, and maybe even they live elsewhere, they can be expanded on those on the principal series. But since principal series seems to play such an important role, is it possible that in the context of celestial sphere, it's actually the conformal partial wave expansion that's more relevant?
But in normal CFTs that you have in mind, I thought that this partial wave expansion with a contour trick, it gives you all the conformal blocks. So there's more like,
yeah.
So here, of course, we have the, I think Anastasia found in their paper where they did conformal partial waves, that if you continue this trick, you will find actually conformal blocks that have complex, if I remember correctly, spins, complex, excuse me, dimensions. So basically they have dimensions that belong in the principal series. And that was the paper back in 1904. I mean, 2019. So it seems that this is, if you had a normal CFT, when you do the contour trick, you will get only integer spins. And if it's unitary, the theory, you will get all integer, excuse me, dimensions, you will get only positive ones if the theory is unitary. But here, if you do the conformal partial wave that I think Anastasia did back and Anders some time ago, you will find dimensions that they're not positive. You find complex ones. So in our perspective, all these dimensions that seem to play a role, these representations, they seem to be operators we need to include in the theory. So the one does not exclude the other, that's what I'm saying. I don't know if I answered your question or what I think at least, but you can do conformal partial wave expansion, but if you do the same things you do in standard CFTs, you will find operators that belong in the principal series when you close the contour.
Right, but I believe in both cases, in both the ordinary CFT and the celestial CFT, we can do both. And as you said, they're related by deforming the contour. But is it clear which one is more relevant in the context of?
Let me jump in. The point is that we never, the form of the conformal block is the Osborn. I'm talking about Osborn's block.
Right.
Okay? So we don't do any integrals. We just use we have the 4-point correlator, and by using essentially Gauss's recursion relations, we are able to write the sum over conformal blocks. So there's no integral. There is nothing here which there's nothing sophisticated. You can do hand by hand by using recursion relations. So I don't know. So I'm confused what I'm doing with two expansions. I mean, there's one. I know I can give you unique expansion of the 4-point correlator in terms of Osborn hypergeometrics, which represent conformal blocks.
Right. So that's great. But on the other hand, the same function can also be expanded on a different basis, namely the conformal partial waves.
Yeah, but I thought that this basis doesn't give you the physical operators. And I think that's explained in a paper by Wheaton and Simmons-Duff in 2017.
Well, in ordinary CFT, yes, but is it clear that they don't give physical operators for celestial CFT?
Yeah, I think it is. I think it's clear that it should be a complete it should be a complete basis of states, right? And the unitary principal series can't be a complete basis because it's not closed under the operator product expansion.
Well,
so the hope would be that there is some complete basis and you compute their 4-point functions and you get a sum over conformal blocks, and that includes some set of states that is closed under the operator product expansion.
Well, but I thought even though when I fuse two states from the principal series, I go outside the principal series, but then I can expand them back to the principal series.
Mm-hmm. Yeah, I'm also confused by the statement that it's not a complete basis.
You can expand them back on the principal series.
But may I add something which is, I think it's trivial, and Sean already kind of said it, but you can, any conformally invariant function you can expand on in a complete set of whatever in conformal partial wave. But I think, okay, at least I think most of us believe that these celestial correlators
have some additional nice properties. They're not like any function of Z and Z bar, right? At least they obey some crossing relations inherited from like crossing symmetry in the bulk and so on and so forth. So I think, perhaps I would say that one should perhaps hope for more than just a partial wave decomposition of these objects. So yeah, I'm not sure if you agree, but
yeah, but
I think also when you do this partial wave decomposition, when you try to close the contour, you don't close exactly on the principal series. You actually get operators that have real part which is bigger than one. So it's obvious that you get more operators, which seems to be something like what we got in our recent paper in a sense. So you get more than that. You don't get just the principal series. And again, I would cite the paper by Anastasia. I mean, as a first example, and of course, I'm not sure in the one with Andy and Anna Maria, they had something similar, but you in your expansion, you do get operators that have integer dimensions, if I remember correctly, and light ray, right?
Yeah, and you're also getting bi-adjoint, right?
Right, yeah,
so there's no, you can't interpret that as a
principles, yeah.
Yeah.
Yeah, so I think so here the correct thing is you can use it as a tool, the partial wave expansion, but at the end I think you should go exactly to what Tom said, like to do conform.
Yeah, I'm curious if you could do that. We didn't do this exercise, but it should be a straightforward exercise to just check. We have conformal block coefficients for many amplitudes, shadows, non-shadows, okay? And they're all done as the same technique, which is you just reshuffle hypergeometric functions and so on, and then construct, express in this Osborne basis. I'm curious what happens if you try to you could also try to do contour integrations, yes? So that would give you a hint. You should be able to reproduce this result by using these techniques with contours, and that will give you a very clear answer. What is the prescription you would call in this way? Yes.
Yeah. Certainly.
Yeah, that should work. So I want to ask Shamik something. I'm a bit confused about the symmetry. You use Virasoro. Can you please say a bit more on that? You use Virasoro on one side, and what was the other? The left movement?
This is the SL2C bar algebra. So that was actually used. The Virasoro actually has not played any role, but it is there. So that we missed at first, but then actually after some discussion with Andy and so we just went back to that, and so that symmetry is there. So it's a symmetry of the OP. But as far as the null states are concerned, actually, so Virasoro is not playing any role. So it is only the SL2C bar current algebra and the super translations. So,
right. So the SL2C bar, it's not the global of the one. It's a cut mood. Is that correct?
Yeah. Whose global part is essentially the SL2C bar, in the sense that the L naught bar and L bar plus minus 1. So that's what they mean by the SL.
Thanks. Yeah, that's like thank you.
More questions, comments?
Sabrina. I think Sunhe would say a few things more about disconnected parts, right? Of the I would like to hear that, because I'm a bit also confused what's happening with that situation. mean, that doesn't play any role in the conformal bootstrap, this thing, does it? Or usually we compute it on the connected part, right?
No, in ordinary ADS CFT, right? If you have a free scalar in the ADS bulk, a massive free scalar, no gravity, just a free massive scalar, right? Then the boundary dual is a generalized free field CFT.
Yeah.
And in the bulk, all the Witten diagrams are trivial. They're just product of the 2-point Witten diagram. And indeed, that's the disconnected amplitudes, and that's the leading large N answer in ADS. Right? That's the ordinary large N factorization. So I would say in ordinary ADS CFT, the disconnected amplitudes in ADS is what gives rise to the leading large N result. And yeah, I think it will be interesting to explore analog of that for celestial holography.
Mm-hmm. Okay, good. Thanks.
Yeah, I'll say a little bit about that in the panel discussion tomorrow.
That would be interesting.
Yeah, thanks.
Emilio's here, right?
More?
Yeah, so yeah, I had a question again. That goes to Emilio. Maybe I'll bring it up at the end of these things. So I understand. Hi, Emilio. Sorry, I keep closing the video because of my. Yeah, so I understand that your conditions. I mean, you had a section where you are computing the Hermitian conjugates of L1 and L bar 1, and they are kind of related left and right movers. So I wonder how come we have a CFT that has left and right movers if you are basically by Hermitian conjugation, the left moving states, if I remember correctly in the norm, they're related to the right movers one, right? I'm a bit confused. This was actually, again, I don't know if I said it correctly, but can you say something about that?
So I guess that this is probably something kind of related to this shadow option for the in and out state. Yeah. So, well, the point is that if you naively want to define your generators, let's say Li, from the 4D bulk, then you get that the conjugation that you get for these are not quite nice, and indeed I don't know, it's you don't quite get something that satisfies some. Even just the state that you get don't have the right properties that you would expect in a CFT, like having some nice radial quantization kind of structure. Right. But yes, so I would say that probably indeed this kind of shadow transform is needed, or something on this line. I don't quite know.
Okay.
So I would maybe say that yeah, to do some to find in from out state, you probably need to do some shadow. This would be my guess.
Right, which is what Andy did, I think, in a recent paper, right?
Yeah. But even though I'm not sure if that was done on all the in and out. I mean, when you conjugate, I would imagine that you should. I think, for example, for this disconnected case, it's gonna be kind of. I mean, you would get some delta function for each 2-point. For each 2-point is a delta function. So if you do not do a shadow at each point, you will never get some power law. So if you get instead, if you do this shadow at each point for for the like conjugation, then you do in fact get something that looks like some generalized free theory. So that for the disconnected, it's kind of telling you that maybe this is the good recipe. But the problem is like these are nice ideas, or like, but before like trying to push them, one would like to have some 4D interpretation of this shadow transform instead of trying like just to define it and see what happens. So that I don't know why it's the good prescription.
I have a quick comment, but I agree with what you said for the massless scalar. But of course, for massive scalar, then you will automatically have both the power law and the contact term.
Okay, indeed. Yeah, you're right.
Yeah.
If you are talking shadow, then that is actually a right place to ask the question about shadows. So if I understand, so you start from a primary field, yes, and it's a Virasoro primary, not a global. It's global, but it also Virasoro primary, we believe, yes. Yeah. So now, on the other hand, you perform the shadow transformation, as I can tell. You don't know whether it's Virasoro primary. You know it's a global primary. So is there any type of, my question is there any type of shadow transform which is covariant, or that's related to the question if you start playing with moving this interpretation of some state should be shadow, some shadow. I think that sort of that's something which I'm not comfortable about, yes, because it is, it's not obviously it doesn't obviously Virasoro covariant.
And that I don't know about, we didn't try with Virasoro. I don't know, maybe there's something similar, but I don't know. Also, I would like to say that this, I don't know, we were not expecting that. I mean, let's say that in higher dimensions, if you study some primary descendants, at least the ones that are studied, for example, I'm quite sure that in odd dimension, it's probably not possible to find these shadow relations between primary descendants. I don't know on maybe in even dimension they exist. So I don't know. It depends on indeed on the algebra that you're studying, and I don't know for Virasoro if there is something, some generalization of that. So yeah, one can try, but yeah, it's so you see this structure of a submodule, like where you have a model that is singular and it has another submodule. I mean, this is actually well studied in representation theory. And so, for example, actually there are always this nested structure of singular models, even in higher dimension. And just to, so that they have a linear shape though in odd dimension. So while in even dimension, you always get some diamond with some, let's say, necklace that is on the two sides. Maybe it's a bit hard to explain this, but let's say that this for this kind of structure, I think it's important that you have this submodule and this nested representation. And yeah, I don't know how it works for the Virasoro case. So yeah.
I mean, a lot of the discussion here has been about scattering of, gluons or whatever. And if you, like in ADS, if you start with ADS3, say, if you start with, a scalar field, the primaries sitting in the middle of ADS, you do any SL2R transformation, that gives you a complete set of normalizable solutions of the scalar wave equation. Then if you're acting with the SL2R, yeah, SL2R times. Then if you act with the L-2, you're adding a graviton to that. Mm-hmm. So the same thing is true here, right? So if we want to start talking about Virasoro transformations and acting with invariance under L-Ns, then we need to be having a discussion about scattering amplitudes with a lot of endpoint, higher point with soft graviton insertions.
More comments? If not, maybe we can close the discussion. Do you guys have anything to say? Like I'm talking about Stefan, Anglos, Andrea. For people who are here, maybe for the speakers of the day, if you can please send us the slides so that we can post them. We will also send you an email, but feel free to send us the slides. So we will make them public together with the recordings.
I just want to say that it was an excellent discussion, much better than a session of strings.